In this lecture, I am going to go through another example problem with half-lives. In this one, we're looking at iodine 131. So this is a radioactive isotope that undergoes a chemical reaction that's actually a nuclear reaction. And it has a first order decay nuclear reaction, which means the reaction is going to have just a first order reaction rate. And it's going to have a half-life of 8.07 days. And what we need to find out is what's the amount of time that's going to pass before that concentration of iodine 131 that we start with falls down to 1% of the initial value. So we really need to see when we go from 100% iodine 131 down to 1%. So let's write out some of the equations we'll use. Now we know our half-life is 8.07 days. We know that that's going to be equal to 0.693 divided by K because this is first order. We also know the other equation that we're going to use is the natural log of our concentration at time t divided by our initial concentration is equal to negative KT. So that's our integrated rate law for first order reactions. And then this 1%, the initial value, we can use that to make our an equality between our concentration at time t, which we're interested in. We're interested in when is t. And so we know that at time t, or our concentration is going to be equal to 1/100th, or you could say 0.01 of our initial concentration. So we can set up that equality that we can plug in here. So our big goal here is to figure out time. And so we're going to be looking for this piece right here. And we're going to need K, which we don't have, but we can get K from our half-life expression. And we know our half-life for this. And so then we'll also use this value here. Let's use this equality here to substitute in here. So let's go through this and first find K, and then we'll find T. So our half-life is 8.07 days, equal to 0.693 divided by K. Rearranging this equation and plugging into my calculator, I learned that K is going to be equal to 0.08587 inverse days. All right, so I can plug that into my rate law, the integrated rate law. So I'm going to set up my integrated rate law now with this information of K and also substituting the concentration at time T for 0.01, the initial concentration. So I'll have the natural log of 0.01 of my initial concentration, so that's for time t, divided by my initial concentration. It's equal to negative 0.08587 inverse days times t. So these initial concentrations cancel out in this equation, and this simplifies to the natural log of 0.01. And I can divide my negative K on each side. So that way I can isolate T. So I'll have negative 0.08587 is equal to T. And now this is something I can easily plug into my calculator. And when I do that, I get a value of 53.6 days.